Okay, then the y-test, it works for bivariate and multivariate regression. And then this is the steps, and it involves chi-square distribution. So we first run the regression. It could be bivariate or multivariate regression. Then we extract the residuals from this original regression. Then we derive the square of residuals. So expect the square of residuals again is regarded as the proxy of variance of error terms. And now this is the confusing part. We run another regression, auxiliary regression, square of residuals as the dependent variable, and then regressed on the following independent variables: the original values of explanatory variables, the square value, and the cross products. This is the step that is so confusing, and this is why I explain it clearly in the study guide. So let's look at this. Maybe let's look at the last case, the multivariate regression. Do you notice? Let me enlarge that. If this is my multivariate regression, y as a function of a, b, and c, three explanatory variables, then how would my auxiliary regression looks like? Remember I said we extract the residuals and then residual square. Okay, it is a function of the original values, a, b, and c. And then we go back to the slides, original values. I'm done, a, b, and c, the square value. So it means a square, b square, c square. Happy with that? This is what square value means. And then the cross products, it means the product of each pair of explanatory variables. This is why you have a times b, a times c, and b times c. So are you happy with this? So in other words, in case this multivariate regression has got three explanatory variables, then for the auxiliary regression, there are, I think, a total of 9 explanatory variables. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 explanatory variables. It means k parameters will be 10. Remember, you have to add the constant back. And the next case, if the multivariate regression has only 2 explanatory variables, a and b, and then I extract the residuals and then residual square, then how would the auxiliary regression look like? So residual square is a function of original values, a and b, then the square value, a square, b square, and then finally cross product. There's only one cross product this time, only a times b. So in this case, there are a total of 5 explanatory variables. Happy with that? Or the number of parameters k is 6 if we include a constant. Then the last one, what if the original regression is a bivariate regression, which means y as a function of a, then the auxiliary regression would be residual square is a function of the original value a, and then the square a square. And then there's no cross product because there's only one explanatory variable, so no cross product. Okay, so I hope you are happy with the explanation. Okay, then we can go back to the slides. Okay. And then for this auxiliary regression, we would conduct the y-test. Again, new hypothesis, homoskedasticity. Alternative hypothesis, heteroskedasticity. And again, the goal is that we do not want to reject the new hypothesis. And this time, this test does not involve t-test, not two-sided t-test, but rather it involves chi-square distribution. First, we have to calculate n times r squared, but you must substitute the right r squared. The r squared must come from the auxiliary regression, not from the original regression. And then we have to look for the chi-square statistic. The degrees of freedom is actually the number of independent variables in the auxiliary regression. Okay, and then if n times r squared is greater than chi-square statistics, we sadly reject the new hypothesis. So let's do this question. This is my original regression, multivariate regression, A, B, and C. And then we extract residuals and then residual square, which is regress on A, B, C, A square, B square, C square, then the cross product, AB, AC, BC. Sample size 33, K 10 parameters. So K prime actually stands for the number of parameters excluding the constant. This is why K prime equals 9, which is actually the degrees of freedom when we look for the chi-square statistics. R square of the auxiliary regression, I must give it to you. So now the point is, I will confuse you. I will also give you the R square of the original regression to scare you a bit. I want to see if you would substitute the right R square. for the y-test. So the new hypothesis, alternative hypothesis, you should be fine. N times R squared, 33 times 0.122. You must substitute the R squared from the auxiliary regression, 4.026. Chi-square statistic, alpha must be given to you. 5% degrees of freedom is K prime, which is 9. So if we look at the chi-square table, 5%, 9, so 16.919. Happy with that? Okay. 16.919, and since n times r squared, luckily, is smaller than the chi-square statistic, so the good news, new hypothesis is not rejected. So in other words, the error terms in the original regression, y as a function of a, b, and c, the error terms have a constant variance. So in other words, heteroskedasticity is not present, or we can say homoskedasticity is present in the original regression. So this is the y-test. So to summarize, Park test works for bivariate regression, two-sided t-test. Spearman's rank correlation coefficient test works for bivariate regression, two-sided t-test, and then the y-test works for both bivariate and multivariate regression. But if I ask question on the y-test, I would mainly focus on multivariate regression with 2 or 3 explanatory variables, and y-test involve chi-square statistic. And in all 3 tests, the goal is that we do not want to reject the new hypothesis. Okay? And then the last one, the weighted least square. Okay. I think if you know this slide, it would be enough actually. But I also explain it nicely in your study guide, so let me rather open the study guide. Okay, so the story is as follows. This is my original regression, y as a function of x, but unfortunately heteroskedasticity is present. So we want to transform the x and y and rerun the regression so that we can get rid of heteroskedasticity. And luckily, for the weighted least square, we have to know the variance of the error term at each x values. I know it is hard for it to happen, but we just have to assume, according to this theory, weighted least square, we assume at each x value, we know the variance of error terms. And then we need to do some transformation. We must derive x asterisk, which is x divided by the standard error of error term. And then y asterisk, which is equal to the original y divided by the standard error of the error terms. Okay. Standard deviation of error terms, sorry. Okay. In other words, we actually weight each x or y value with this sigma, standard deviation of the error term, and this is why this remedy to get rid of heteroskedasticity is called weighted least square. And then we rerun the regression as y asterisk as a function of x asterisk. And in this transform regression, we argue that we successfully get rid of heteroskedasticity. In other words, the error terms are now constant in this transform regression. Okay, and then this is just a numerical example. This is the original x, variance of error term, and then the square root of it. Square root of 4 gives you 2, square root of 16 gives you 4, and then the transformation, the transform x. This is why we have 1 over 2. I should actually enlarge it, actually. Okay. 1 over 2 gives you this answer, 2 over 4, 3 over 8. So happy with this column? And then this is the other transform variable, the y asterisk. Okay, 10 divided by 2 here, 12 divided by 2 here, and so forth. And then the last one, 20 divided by 8. And then we run this regression, y asterisk as a function of x asterisk. Then we argue that for this transform regression, the error terms finally have constant variance. In other words, homoskedasticity finally happens. Okay, so that's it for chapter 11. Then the next chapter, chapter 12, is autocorrelation. So see you then.